Okay, this is so lecture 00. Okay, we are lecture 11 about the drift diffusion model. And okay, so if you are in trouble with previous homework, then it is allowed you to do your homework with your schedule, but please note that we have a due, so the later submission will not be counted as a proper submission. So but anyhow, you have to do your homework, because this is the system of our homeworks are really incremental. So if you cannot finish one previous homework, then maybe you will have continued trouble in doing your next homeworks. So please try to keep up the progress of our homework. Okay, so now let's go to lecture 11. So what was the content in lecture 10? At the time we have thought about so-called drift diffusion model. So here we have drift and diffusion. So drift and diffusion. So although we say this is a drift diffusion model, however, if we consider just three equations related with this drift diffusion model, actually the equation itself or equations themselves are not directly related with this drift diffusion scheme. So maybe you remember that this is the original form we will use, and also we will consider the continuity like this. So here we have Q and divergence of electron current density vector, and also we will have something like this, so minus Q. So here we have different in polarity or sign only due to the difference in charges carried by our electrons and holes. Anyway, this is the form of drift diffusion equation. However, it does not specifically say that drift and diffusion. All of that information is just hidden in this part, Jn and Jp. So the name, the drift diffusion model, comes from that, since we have assumed the form of Jn and Jp as this one. So Jn and Jp are represented as just a sum of drift term and diffusion term, and drift and diffusion term. Of course, you can say that then is there any alternative way to present this Jn and Jp? Yes. So for example, I have to say that drift and diffusion, the point is we can have additional forms here. For example, depending on temperature gradient, maybe that would be the most significant form. And also, if we are going to extremely high frequency, then even we can have some convection or convection-like terms. So that is more or less proportional to the second order of electron speed, or in this case hole speed. But anyway, so we have this nonlinear term here, and yes, this is a temperature gradient. And when we consider temperature gradient, even this drift term and diffusion term, they are affected by this temperature gradient or spatial distribution of the lattice temperature over this one. So yes, so simply speaking, so drift diffusion model can be regarded as the simplest one among the family. So we can sort about different different equations, and they can be categorized as just one family. However, in this work or in this semester, we will just consider drift and diffusion terms, so all other terms are neglected. And if you remember correctly, then that has quite a simple form, easy to remember. it was q mu n e plus q dn and gradient of n. So how can I memorize it, or how can I remember it? So it just comes from my repetition for writing down this equation so many times. So I hope that you both all of you can also follow the same fashion. So dp and dp. So here we have different signs here, but maybe at the first glance it seems a little bit different, difficult to understand. So this is related with diffusion, and diffusion is solely given by the gradient of our carrier density. So at first glance, maybe some students can think that, oh, for diffusion term we have to have the same sign. On the other hand, if we consider a drift related term, we have the same sign, the positive sign. But you know that when we have a given electric field, then motion of our electron and hole is the opposite. So electron is just attracted by the electric field, and the holes are following the direction of electric field. So if there at the initial time, if we have two electron and hole at the same time, then they will separate it if electric field is given. So therefore the same sign here related with drift and different sign in diffusion related term can be, so there's a real paradox. But please note that we are not talking about the flux itself, we are considering the current density. So the simple answer is, okay, this quantity is given by minus q times electron flux, and also this Jn is obtained by positive q multiplied by whole flux. So initially when we consider just the fluxes, then yes, as we expect, the diffusion term has the same sign and drift term has a different sign. However, since we have applied or multiplied different sign quantity, minus q and positive q, that's the reason why we have different signs in here. So please remember these sign differences. So, and yes, so the next topic we will consider is usually how can we discretize it. So, but before talking about the discretization, I wanted to give you some simple note about implementation. So yes, implementation. Here we have three equations, and maybe you may think that, okay, this is another two equations related with j sub n. So what is the quantity of our interest? Yes, so we can find the displacement vector, which can be written as like minus epsilon. Yes, you may have this form, and electron density, hole density, and electron current density, hole current density. And here you have hole electron and hole current density, and also here N, P, E. E is related with our electrostatic potential, and also we have NP. So you may think that, okay, so as a result of this all kinds of collection, so finally we will have 5 equations to be implemented. But you know, this is not the case. So usually what we do is, although we have j sub n and j sub p here explicitly, so what we do in reality is just to introduce j sub n, j sub p in this continuity equation. So you will have q mu n n e plus q dn. Yes, that will be the form we will use also yes mu p p minus q dp. So if we explicitly use the form of current densities, so J sub and J sub p are explicitly written here, then we can certainly say that these three equations are well related with drift diffusion scheme, because the current density itself contains both of drift and diffusion term and only contains those two terms. So that is really the drift diffusion model. Okay, so also maybe, although not I have discussed up to now, you can easily understand here d is given by minus epsilon ln phi. So instead of the vector quantity like d or e, we can always think about scalar quantities like phi, n, p, also n, p, n, p, and this electric field can be also given as what? Given as minus gradient of phi. So you can say yes, here you will have this form. Also here you will have this form. So you will have this form. So all of our unknown variables are just scalar unknown variables. There is no vector field itself comes in. So if you really wanted to calculate your some vector quantities like electric field or J sub n or J sub p, then once you get the solution out of this coupled system, then you will have phi and n, p as functions of the position. Then from this one you can readily calculate those quantities, because you know the definition or the expression assumed in your work. So it is not that difficult to calculate all of them. Okay, so guys, do you have any questions?
교수님 혹시
Okay.
지금은 그 파이 MP가 이제 그 드리프트 디퓨전이나 그러한 그 이퀘이션을 푸는데 사용했는데 혹시 이제 홈워크 10에서는 저 드리프트 디퓨전의 식이 아니라
Okay.
그
So we have used alternative form.
예, 일렉티브 그 덴시티를 구하는 그 이퀘이션을 푸는 걸로 컴퓨터를 했어야 되는 게 맞는지.
Yes, sure. So this is general drift diffusion model, and in our homework number 10, instead of this general one, we have introduced a system which is strictly valid at equilibrium, only at equilibrium. So yes, you may remember this one is your equation at hand. Yes, so and p is given by n t. You know, these or those expressions are valid at equilibrium, and also we have additional approximation. So in order to have such kind of expression, then we have to adopt the Boltzmann statistics. So you know that. So we have two different statistics appearing in this field. So Fermi-Dirac distribution and Maxwell-Boltzmann, and we have to follow this guy. Then we can have this expression, but you know that at the first trial, Maxwell-Boltzmann statistics is not that bad, so we can have this form. So the reason why, or the motivation I gave you this example instead of this fully functional one, was just to give you some time to prepare three equations. So in many cases in our previous lecture, students are just experiencing some implementing just one single variable equation, or at most two variables equations. So however, the number of unknown variables can be large, not like just 2 or 3. In many cases it can be, for example, 4 or 5. So typical way we have 4 equations in our advanced simulation is just introduced to you. So what will be the unknown variables in our case? So here we have of course electrostatic potential and electron density and hole density, and say that you are working with, for example, FinFET simulation, or some cases you can also try to, for example, even more advanced one, CFET or something like that. Then you feel that, oh, okay, so here we have strong quantum confinement, then those quantum confinement effects should be considered in our simulation. Then how can you do that? In that case, in addition to those 3 equations just introduced to you, so boson equation and electron and hole continuity equation, usually you have to solve additional equation for quantum confinement. So the typical way we adopt is density gradient equation, and this is the equation, and from this density gradient equation we usually have additional unknown variables. So I don't think that there exists a standard symbol for this quantity, but anyway, for example, let's call it as a psi, and yes, then it can be, for example, quantum potential, or sometimes people say that use just phi, but say quantum potential, or I have no idea, or sometimes they try to introduce this capital letter, but whatever. It is true that we have to introduce other quantities which can be a function of position. Yes. So, for example, we have to introduce this quantity. Then the total number of unknown variables can be increased easily from 3 to 4. And of course, you may say that, okay, then why don't we have 5? Why we have 4? Usually in order to reduce the computational burden, if you are talking about the NMOSFET, then usually you consider quantum potential for electrons, and if you are simulating the p-type p-MOSFET, then usually you consider just the quantum confinement for your holes. It is because they are inversion carriers, and only inversion carriers experience strong quantum confinement effect. So in the case of NMOSFET, usually holes are just leave it as it's a bulk state, so we don't have to think about the quantities like a whole quantum potential. So this is one thing we can expect from our experience for FinFET. And also, if we are talking about other types of devices, like for example, power devices. So if we have power devices, then we can have internal heat generation. So heat generation inside the system at a point can be easily considered like this. It will be just proportional to J times electric field. So you know that if we are talking about some element-wise manner, then power dissipation can be written as a product between current and voltage. So that will give you the power dissipated by a certain element, and you can easily find that this is point-wise expression for your power dissipation. So therefore, it can be regarded as how can you say density of power dissipation. And when we have such kind of quantity in our mind, then if we have a strong power conduction for our power device operation, then we can have a large power dissipated inside our device. Then what will happen? If that such amount of power or heat is generated by our device operation, then that heat should be disappear anyhow or transferred to the more cold part of our system. So usually we can think about this point of view. We have a hot place where really strong current conduction is observed and there is a large potential difference. So in this part we are having really hot distribution, and from far away from that point, so we have a cold part. Okay, I don't care about actually the operation of our device, so this is just kept as 300 Kelvin. Then what will happen? Yes, this part is really hot and this part is really cold, so we will have the transfer of heat from that hot part to to cold part, so heat will be transferred. Then how can you support that kind of heat transfer? Heat transfer can be maintained by just having difference of temperature. If we have the same temperature, then there will be no heat transfer. So we will have a heat transfer, and yes, the temperature will be elevated. It is quite easy to understand. There occurs a lot of heat generation. So locally for that part, we have the heated region, so temperature is going up. Then what will happen? Previously, in many cases, we just assume that the temperature is constant over our system. For example, 300 Kelvin, many cases, or 350, or yes, anyway, we are just in many cases, in conventional cases, we use the constant temperature. However, if we consider such kind of situation, self-heating, so-called self-heating, then we have to consider the temperature of our lattice as a function of position. So this part we have 350, and here we have 320, and here we have just 300. Those calculations should be done. If we have to do that, then usually we have to introduce lattice temperature. And I remember that we have talked about even further examples like electron temperature and hole temperature in the case of really heated. So heated means that this is the heating of our lattice, and these are related with heating of our carriers like electron distribution and hole distribution. So the difference between these three concepts should be well understood by you. So if you don't understand the differences, then please let me know, and I will try to give you more explanation about differences between them. And this is quite important concept for certain thermoelectric devices. So in thermoelectric devices, that is the difference between temperatures that really at the heart of its operation. So we have to consider those quantities. So now you can understand. Yep.
혹시 그러면 캐리어 온도랑 lattice 온도가 뭐가 어떤 게 선행돼서 그렇게 값이 변형된 건지?
Yes, you are right. So if we are talking, that's a really good question. If we are talking about self-heating case, many cases we are talking about self-heating case, then energy is usually stored in our electron. So first, electron or holes are heated. After that, that energy, additional energy, is dissipated to the lattice. So what is it? How can we transfer our energy stored in electron system to the lattice system? That is, we call it as phonon. So that is the basic mechanism to deliver our energy from carriers to lattice. Of course, if we have such a case, like even the lattice temperature is higher and carrier temperatures are lower, then what will happen? Then in this case, again by using these phonon scattering mechanisms, then our lattice will try to heat up our carrier system. So yes, always we wanted to have the same temperature because they are talking to each other. However, in many cases, so the electric field, the energy stored in our potential energy, is first transferred to the carrier system, and after that, after some time later, so the characteristic time will be the scattering, will be determined by the scattering rate, phonon scattering rate, and that will be related with this system. So I can say that, simply speaking, the journey of our energy is, here we have electric potential energy, and that is transferred to the electron system by acceleration of our carrier. After that, that will be converted into or transferred into the lattice system. And what happens to this lattice system? Lattice itself has phonons for having the energy, and phonons are usually considered as quite fast. So if we have different temperatures in this part and this part, and this part is hot, it means that we have a lot of phonons here, and here we have a cold. It means that we have a relatively low number of phonons. Then this phonon will diffuse. Then diffusion of this phonon is regarded as a heat transfer. Also, that is our view. So we will have this kind of a diagram starting from potential energy to lattice temperature. So if, for example, if our system has really good, how can I say, really good, strong connection between carriers and lattice, then maybe we can assume that those two quantities are quite much related. And if we have almost no phonon scattering in this case, then maybe they can be quite different. And one thing which makes our problem even more difficult is the phonon is not a single body. So although we say that phonon, but we can also define different phonons. There can be different phonons, and typically we say that there are optical phonon and acoustic phonon. So when we send our energy, then usually the energy is sent to acoustic phonon, because acoustic phonon has a considerable energy in our semiconductor system. Like it has, for example, the most representative optical phonon has typical energy like 60 milli electron volt, and acoustic phonon, no, its energy is much smaller, like just a few milli electron volt or even smaller. So if we consider the energy transfer from electron system or whole system into our lattice system, usually this optical phonon takes all. Yes, the energy is first stored in this optical phonon. After that, however, unfortunately, this optical phonon is well known that it is quite slow, and almost it does not move because it has its how can I say, dispersion relation, EK diagram, and it has a very smooth curve here. So the slope of this EK diagram is related with the group velocity of that kind of quasi-particle. So we can say that, oh, optical phonons are awfully small or awfully slow and it doesn't move at all. Then how can we just dissipate the energy stored in a certain part as a form of this optical phonon to external world? It can be done by this transition. So optical phonon can be decomposed into this acoustic phonons, not decomposed, but it transfer the energy to several acoustic phonons, and they are fast. And once that takes the real energy, then they immediately escape from that part. So now we have the loss of energy at a certain point. So initiated by Mr. Park's interesting question. So that is the view related with the heat transfer inside the nano electronic system. So usually we think that, okay, Tn or Tp are larger than temperature. Also this lattice temperature can be a function of position. That is the thing we can expect from our simulation. So anyway, let's come back to our main discussion. So the initial question raised by Mr. Park was, okay, should we consider general number of unknowns? Yes, we have to, because the number itself can be changed quite dramatically. So also, even for same system, let's say that there is a certain device. So for certain device, we can apply so many different set of equations. For example, we can solve it with just simple Dirichlet diffusion model, and we can also solve Dirichlet diffusion model with quantum potential, or we can solve Dirichlet diffusion but modified with lattice temperature, so plus some heat transfer equation, or. And in many cases, actually solution of these additional or more complicated set of systems can be obtained only from the solution of our Dirichlet diffusion. Okay, so once we solve just isosomal Dirichlet diffusion model, then we can allow the temperature variation. Otherwise, sometimes the system becomes too non-linear, so we will have some convergence difficulties. So, simply speaking, when you start your simulation, oh, my ultimate goal is really electrothermal simulation. So, I will just make a code which is strictly valid only for electrothermal simulation. It is not possible. Actually, even though your goal is ultimately electrothermal simulation, but during your journey to that simulation result, in some part you have to do just conventional, tedious Dirichlet diffusion model. So, simply speaking, please try to separate the concept of device and equation. In this semester, we are trying to make a distinction between different concepts, like structure. Structure should be just separated from your own implementation. If you have to build your system for every example you have to consider, that will be a nightmare. Also, now we are talking about equation. Your equation can be fully set by the users. Oh, I wanted to just solve simple nonlinear Poisson equation, or I just wanted to solve standard Dirichlet diffusion model, or sometimes, oh, I can spend more computational resources then I can solve one additional equation for this system that should be available to the users. So you as a developer should allow the freedom to choose the set of equations to users. Okay, so therefore you have to say that structure, which can be loaded from the external file, and equations can be set by the users, and also here you have your own implementation. So here you have to have the concept of a device. So device means that should be regarded as a container for your unknown variables. Your physical quantities should be stored. So your phi, your n, your p can be just stored in the device. However, device itself is just regarded as a container. Then what happens when you means that in this case when the user try to solve something, then they just combine this device and equation, then you will get certain set of equations, and as a solution of that system you will get physical quantity that those physical quantities will be stored in your device. It means that once you introduce additional equations, oh, I wanted to solve a different one, then these equations will be gone. It is no longer valid. So previously I was interested with those equations, but no longer I'm not interested with electrosummer simulation. Instead of that, I will just consider, for example, stress dependence of our property. Then what will happen? In this case, you have to build your new equations and build a new set of equations, and you will get different solutions. Of course, there is no guarantee that you have the same solution, but anyway, that should be the progress of your code. Of course, I'm not asking you to build such kind of a complete system, but anyhow, you have to keep in mind that the commercial or some advanced device simulator should support those concepts. Otherwise, it would be really difficult to users use your code. In many cases, you just build the code for yourself, so you don't feel any difficulty. But if you are really care about your users, then you have to consider those considerations. And do you have any question?
그러면 스트럭처랑 이퀘이션이 외부에서 주어졌을 때 그 계산을 이제 계산을 통해서 디바이스의 그 베리어블 퀀티티가 포함된 거를 이제 제작을 하는 걸로 이해를 했는데 만약에 그러면 그 계산을 하기 위해서 자코비언이나 레지듀를 구성할 때는 기본적으로 그 스트럭처에 대한 스트럭처의 정보에 대해서 의존적으로 그게 고려가 돼야 되는 게 아닌가?
No, that's the point actually. So when we have an arbitrary input structure, your code should be able deal with those arbitrary structure. That is the point. So I think that your difficulty in solving our previous homework is all related with that concept. So how can you generate such a kind of general implementation? So then we can, in many cases, we can think about a set of vertices, and we can think that set of triangles in two-dimensional case. Then the number of vertices and the number of triangles are not given to you. So the point is, when you have such kind of arbitrary structure, then first you have to analyze them, then have a certain collection of information. So which one is corresponding to which one in your Jacobian matrix. So which point in your system is corresponding to your Jacobian matrix. It means that table from physical position to the numerical position, that table should build dynamically. So when you have a different structure or different set of equations, then your table should be updated. For example, if you are just solving the nonlinear Poisson equation, then you will have only phi. Then your Jacobian will have a certain number. However, if you just add n and p as your unknown variable also, then the physical meaning of second element in your unknown vector now can be changed. Previously, for example, second element of your second element of your unknown variable vector can be regarded as the phi for your second position. However, if you introduce electron and hole as two additional unknown variables and assign a way like phi and p, phi and p, phi and p repeatedly for each vertex, then maybe this second number 2 can be regarded as the electron density for first node. It is just one example. The assignment can be really up to you. So I mean that even for given structure, when you switch it to from one system to another system, then you have to build this table dynamically. So okay.
그렇다면 그 자코비안의 인덱스랑 제가 그 받은 엘리먼트의 인덱스는 전혀 상관이 없는.
Yeah, sure. So you should have a general relation. So then how can you assign that general relation? It is really up to you. So you have to consider this one. Or one way can be like this. Yes, usually we have many regions. So first learn over your regions. Okay. So I have one region and number of regions. Okay, just to learn over your unknown regions. Then for each region you can have different vertices, so just to learn over vertex. So then you can learn over your number of vertex. Of course, this number of vertex is really dependent on your, how can I say, region. Okay, you can have just 10 vertex for certain region, and you can have 1,000 nodes for vertex for your another one, and you can have, for example, just 3. If you have such kind of thing, then in this part you just set n vertex or integer number n vertex is given by what? Just 10 or 1,000 or 3, depending on your region. Okay, so are you with me? So let's say that this is R1, region 1, and this is R2 and R3. Then the number of vertex should be here. Number of vertex should be taken from, so that for your I region. So you have a certain table containing the number of vertices in each region. So if you have 1, then it means that you are now talking about R1, then your table give you number 10. I have just 10 variable, 10 vertices. And if we go to number 2, oh, then I can find 1,000 nodes, then your n vertex should be 1,000. And if you go to 3, then you have to have 3, because you are now assuming the 3 unknown 3 vertices here. Then now in this case also you can think that, then now you can think that I variable. So 1, 2, n variable. So what is it? N variable is the number of unknown variables. If you are talking about phi and p, then this one should be 3. However, if you just consider just nonlinear Poisson equation, then that will be just 1. So now you have this nested 4 loops. Then now you can say that okay, you can introduce certain count number. Okay, so count equal to 0. And when you first assign your variables, then okay, I can say that region 1, vertex number 1, and variable number 1 is assigned to 1. Region 1, vertex number 1, and variable number 2, for example, corresponding to electron, then that is corresponding to number 2. And 1, 1, 3, that will be assigned to 3. And if we finish this the most nested one, most inner for loop, then what will happen? Now we will have a vertex number 2, 2, 2, and we can just add it up, so count can be increased. Of course, in this is C++ style, so but anyway, you can make your own style using the matchup. So then you can just add up. So learning over entire structure in region wise, then just test whether your variable is really assigned at that region, that vertex. Then if that is really eligible, then assign, and if not, then do not assign. That's all. So for example, let's think about this one. Unfortunately, for example, R region equal to 3 is corresponding to, for example, an oxide region. Then although our number of variable is 3, so however, for example, if we consider this one, region 3, region 3, and region 3, and say that it's vertex number 1. So anyway, then go to number 1. Potential, okay, then we can think about, for example, how many? We can have 3031, because they will contribute to 30 unknown variables if they have all kind of electron, hole, and potential. Yes. Then after that, if we go to the second line, the third one, third region, so oxide region, and first vertex, and whether electron is defined, then our answer is no. There is no such an element in, or such an unknown variable in our system. Then do not increase your count and just assign some invalid value. For example, you can say that 0 can be regarded as an invalid value, or -1, or any kind of negative sign value can be regarded as an invalid value. So that's it. So then after all of your calculation over, then now you have a table. You can just say that please, for nth node and mth vertex and whatever case variable, do we have any valid index inside our Jacobian matrix or unknown variables? Then okay, your index is 3031, or no, there is nothing like that. That can be answered by your table. That table should be constructed when you first have a structure and equation. It is because when you just switch to another equations, then you have to build them once again. So
그 이퀘이션이랑 구조에 따라서 테이블을 계속 만들어야
of course, you have to do that. So therefore, before starting your own implementation, or just before starting your construction of a Jacobian matrix, first you have to collect the indexes of unknown variables inside the Jacobian matrix. So that part should be done by yourself. Okay?
근데 저희가 그 7번 홈워크까지는 그 주어진 엘리먼트에 대해서 이제 자코비안의 인덱스랑 동일하게 해서 매트릭스를 구성했었는데 지금 이제부터라면 이제 리즌별로 벌텍스의 개수를 정하고 벌텍스의 개수를 정하고 그거에 따른 이제 또 다른 테이블이 필요하고 그 테이블을 걸쳐서 이제 자코비안이 이렇게 만들어져야 되는.
Yes, you're right. So, for example, let's think about this one. Now you are trying to solve Poisson equation for certain element. So now you are considering certain element, which is, for example, in this case, triangle. Then you can think about vertex 1 of your triangle, vertex 2 of your triangle, and 3 triangle. In this case, what you do is, okay, for vertex number 1, let's try to find out the quantities like n at v1 and p at v1. Those quantities are required because you have to build the source term, so net charge density. Then, yes, this number v1 can be an arbitrary number, arbitrary integer index. Yes, so what you have to do is when you really construct the Jacobian matrix, then what you have to do is, okay, I have running over region R, and my vertex index is v1, and my quantity is, for example, number 2 corresponding to, for example, electron. Then if you have previously built table, then if you give this input triplet, then you will have the number like 3 or 31, for example. Then you just assign your equation or your quantities in this way, inside your unknown variable or that one. For example, if you really wanted to know the value of electron, then you have to go to the solution vector of your certain index. Then you will find that number. That number is the number for your p. And if we go to, I wanted to also hole density, then you can just change number 3 and use the same index system. Then you will have, for example, next number. Then just try to find out your previous state, the temporal solution vector. Then there you can find that number. Okay, the 3032 element of our temporal solution is related with this quantity, so I will use that number. So you can easily get the numbers for your arbitrary position and arbitrary variable type and arbitrary region in this way. So that is what you can do.
그렇다면 이러한 컨셉을 가지고 혹시 그 리즌별로 어떠한 자코비안을 먼저 만들고 그 이후에 자코비안을 합치는 방식도 어떻게 보면 저러한 매트릭스 큰 그 자코비안 매트릭스를 만드는데 어떠한 역할을 하는 게 아닌가라는 생각이 컨셉이 하나 생각이 드는데 그렇게 진행을 해도 되는지가 궁금해요.
So it is preferred way to do this one, but please note that so consider usually what I want to ask you is always consider the smallest element you can expect. So for example, in this case, consider just triangle. However, when you consider Jacobian matrix, then always the maximal, the entire Jacobian matrix. That is my suggestion. So usually build something and after that just shift it by amount of something. So small block inside the Jacobian matrix was in former course, like old days course, they tried to dissect the entire system into small subsystems and just collect them after that, finally getting all over. However, this is not, in my opinion, not a good way to proceed, because that makes our implementation quite complicated. So our implementation can be simplified by just adopting this rule. When you consider just equation should be regarded as just a minimal unit. In the minimal unit, I mean that when you consider, for example, two-dimensional structure, then a triangle should be the entire world of your consideration. Then assignment into Jacobian is just a matter of numeric, and yes, it cannot disturb your implementation. So please do it in global way when you assign. Okay, then now so we have a long discussion initiated from Mr. Bak's initial questions, a simple question. Yes, the answer is yes, we have to consider general cases. We can select the equation or configuration of equations, and we have to build a general table from the triplet or even more from certain physical specification, region, vertex, or variable, or something like that. So here, when I say that even more, means that, for example, the variable can have also its own internal dimension. For example, think about the quantity called distribution function. So distribution function can be written as position. Yes, so if we have a function of position, then that's it. However, unfortunately, this distribution function can have also its energy dependence. So internally, although all of them are called as the distribution function, but when we change its energy, then we can have also different quantities. Another example we can think is trapped charge density. So maybe Mr. Bach is now dealing with this quantity, and yes, number of traps. So number of traps site can be really position dependent. For example, for certain position, we can have multiple trap levels, and for another position, we have a different number of traps. So in implementation, so we usually have also internal index. So it is not a kind of double variable, a double precision number, but we can also have here trap index. So what is the electrons trap density in at a certain position R and ith trap? So how about the lowest trap or second trap? That can be also treated as a general one. So internally we can have even further internal degree of freedom. So in many cases, or not many, but in some useful cases, we can have internal loop, but it really depends on your application. So yes, let's come back. But anyway, you have to build a table anyhow. So you have the information about your quantity, then you have to have index. That is my main message. So if Mr. Park have suffered from difficulty, I guess that is all related with this misconception of this table. So without this table, actually it is impossible for us to deal with the general structure. However, we have to consider general structure. So if we don't have it, then maybe we have to consider such kind of some arithmetic form, like learning over 3. Every vertex has 3 unknown variables. So then we will have tons of wasted information, or number of n variable times number of entire vertex or entire nodes. So that is also really not very much smart way to do that. So
지금 추가로 그렇다면 리즌별로 볼텍스 파일이 따로 필요한 건 아닌 건가요?
Oh, no. I mean that region should be shared. Region itself should be shared by the entire structure, because think about this simple bar, and you have the position here. Then if we just specify 2 vertex files, okay, 2 vertex files, then due to the small differences in treating the lowest digit, so least important digit, then we have no idea that this point and this point are treated as the same point. So that's the problem. So we have to say, so it means that, for example, think about this: 1, 2, 3, 4, 5, 6, 7, 8. And later we say that, okay, computer, 2 equal to 5 and 3 equal to 8. Don't forget about that. That is almost impossible. So what we do is, okay, there is 1, 2, 3, 4, 5, 6, and the region 1 contains 1, 2, 5, 6, and region 2 contains 2, 3, 4, 5. Then there is no confusion about some whether this point is really 1 or not. So every index is regarded as a unique identification for unique vertex. Okay. So then please go ahead. Maybe you have other question.
비슷한 질문이었는데
Okay.
완벽히 이해가 되지 않는
So what's your question?
저도 비슷한 질문이었는데
Okay.
그렇다면 리즌 방금 예제에서 리즌 2의 첫 번째 볼텍스를 이제 불러와라라고 질문을 제가 던졌을 때는 이제 이 리즌 2의
That's really good question. Okay, I will agree with you. Yes, so think about this one. Yeah, I think that we are getting more into the point here. So let's think about this extremely simple case, simple example, and say that we have 2 triangles. Then how does it look like? Your vertex y will have 1, 2, 3, 4, 5, 6. All of vertex information will be given to you about from vertex 1 to vertex 6. And how about your region files? For example, your R1 specification, you will have 1, 2, 6. 1 to 6 means that you have a triangle which have vertices like 1, 2, 6, and it simply says that this triangle is belonging to your R1. Okay, so I already mean. Then another one is 2, 5, 6. Then it means that okay, also this triangle is belonging to R1, and say that R2, then you will have in the same way 2 3 5 3 4 5 will be your two files. Yes, this is the vertex file and this is for region file. If I assume that you have implemented in a single file for entire regions, of course you can think about different way. So but anyway, that will be essentially that will be the case. Then if I expect or predict properly the main question raised by Mr. Park is okay, now we understand from this configuration, now R1 has vertices 1 2 5 6. I know it, and here we know 2 3 4 5 will be the number of vertices. So then now let's learn over regions and vertices or blah blah blah. Yes, so we have I region. Then of course that will learn from 1 to 2. 1 is corresponding to R1. 2 is related to R2. Then now next question is, now we have to learn over vertex, and we know that each region has 4 vertices, so we will say that from 1 to something. Yes, or instead of that, let me just make it even simpler. So please wait for me for a while. Let's just say that this is your case. So I intentionally made a change because we wanted to have different numbers for our regions. So 1 2 5 and 2 4 5 will be 1. And how about R2? In this case you will have 2 3 4. Yes, then now we are getting close to the point. Yes, now you know that there will be 1 2 4 5 and 2 3 4. Then number of vertex is really a position or region dependent quantity, so you have to have a query like what is n vertex. So then you have to have a certain table or array like 4 3. Then you have now n vertex. Okay, so yes, then let's enter into your this loop for your I vertex. Then now you have a number 4. However, this I number 4, 1 2 3 4 cannot be corresponding to 1 2 4 5. So for your region number 1, you also have to 1 2 4 5. It's an internal quantity. Also, let's consider the second R2. If you go to R2, then your I vertex will learn over from 1 to 3. However, 1 to 3 cannot corresponding to 2 3 4. So internally you have to 2 3 4. So this is the index for learning index for your regions, and you have to find out the real vertex is given by the I vertex and your table, this guy or that guy. You have to build another one. Then now you can fully understand by using this multiple, how can I say, tables of indices, then at each time you can find the correct value. So simply speaking, you don't have the different vertices. Although your vertices is very user-friendly. User-friendly means that when you have such a system or such a mesh, then you can easily build this system. You don't have to worry about this one. For example, 1 2 3 2 3 2 4 5, and now I will have to consider once again only for R2. I have to define 1 2 3, and I have to say that is 1 2 3, and say that this one, this blue colored one, and this black colored two are the same. That is not a reasonable way to do that, because as I told you before, we have to identify both vertices are identical or not. So it is not preferred way, but instead of that, just to introduce additional indexing system that will make your life much easier than expected, than you initially expect. Okay, so time is up, and we have spent quite much discussion about real implementation. I think that it was really useful to our students about real implementation. So if your implementation is not as sophisticated or not as general like this one, then please try to improve your implementation. So I will not give you the official homework today, so please have your time just to self-improve your implementation. Okay, if you have additional question, then please let me know by just plain communication or any kind of means you can have in our lab. Okay, thank you. Bye. 자.